Find the equation of the geodesics on the right helicoid. X equals to u cos of phi, y equals to u sin of phi, z equals to c phi. Solution: the position vector r of any point on the helicoid is given by r equals to u cos of phi, u sin of phi, c phi, where u and phi are the parameters, which implies r1 equals to cos of phi sin of phi 0, r2 equals to minus u sin of phi u cos of phi c. Therefore E equals to r1 dot r1 equals to cos of phi sin phi 0 dot cos of phi sin phi 0 cos of phi equals to cos square phi sin phi equals to sin square phi plus 0 equals to 1. Cos square plus sin square equals to 1. So f equals to r1 dot r2 equals to cos of phi sin of phi 0 dot minus u sin of phi u cos of phi c equals to minus u cos of phi sin of phi plus u sin of phi cos of phi equals to 0. G equals to r2 dot r2 equals to minus u sin of phi u cos of phi c dot minus u sin of phi u cos of phi c equals to u square sin square phi plus u square cos square phi plus c square equals to u square plus c square. H equals to eg minus f square equals to 1 into u square c square minus 0 equals to u square plus c square. Also E equals to 0, E2, E1 equals to 0, E2 equals to 0, F1 equals to 0, F2 equals to 0, G1 equals to 2U and G2 equals to 0. Now L equals to 2 upon H square G E1 minus 2 F1 plus F2 equals to 1 upon 2H square U square C square into 0 minus 2 0 into 0 plus 0 into 0 equals to 0. M equals to 1 upon 2H square G E2 minus FG1 equals to 1 upon 2H square U square plus C square into 0 minus 0 into 2 U equals to 0. N equals to 1 upon 2H square 2G F2 minus G1 minus Fg2 equals to 2 upon H square 2 U square C square into 0 minus U square C square into 2U minus 0 into 0 equals to 1 upon 2H square minus 2U into U square C square equals to 1 upon 2 into U square C square minus 2U U square C square equals to minus U. Lambda equals to 1 upon 2H square 2 E F1 minus E2 minus Fe1 equals to 1 upon 2H square 2 into 1 into 0 minus 1 into 0 minus 0 into 0 equals to 0. Mu equals to 2 upon H square Ag minus Fe2 equals to 2 upon H square 1 into 2U minus 0 into 0 equals to 2 upon H square into 2U equals to U upon U square C square. Nu equals to 2 at 1 upon 2H square Eg square minus 2 F2 plus Fg1 equals to 1 upon 2H square 1 into 0 minus 2 into 0 into 0 plus 0 into 2U equals to 0. We know that the geodesics equations are U double dash plus L u dash square plus 2m u dash phi dash plus n phi dash square equals to 0. This equation 1. And phi double dash plus lambda u dash square plus 2u dash phi dash plus v dash phi dash square equals to 0. Equation 2. Putting the values of the L, M, N, lambda, mu, nu in equation 1 and 2, we get u double dash plus 0 into u dash square plus 2 into 0 u dash phi dash plus minus u into phi dash square equals to 0, or u double dash minus u into phi dash square equals to 0, and phi double dash plus 0 into u dash square plus 2 into u upon u square c square u dash phi dash plus 0 into phi dash square equals to 0, or phi double dash equal plus 2 u dash upon u square c square into phi dash equals to 0, or u square c square into phi double dash plus 2 u dash phi dash equals to 0, or d over ds u square plus c square phi dash equals to 0. Integrating, we get u square c square phi dash h equals to, where h is any arbitrary constant, or u square c square d phi over ds equals to h, or u square c square d phi equals to h ds, or u square c square whole square d phi square equals to h square ds square. But for any arc on the surface, we have, this is equation 3, for any arc on the surface we have ds square equals to e du square plus 2 f du d phi plus g d phi square, or ds square equals to 1 du square plus 2 into 0 du d phi plus u square c square into d phi square, or ds square equals to du square plus u square plus c square d phi square. Multiplying the both sides of this equation 4, multiplying the both sides of 4 by h square, we get h square ds square equals to h square du square plus h square u square c square d phi square. Equation 5. Putting the values of h square ds square from 3 and in 5, we get u square c square d phi square equals to h square du square plus h square u square plus c square d phi square, or u square c square d phi square minus h square u square c square d phi square equals to h square du square, or u square c square whole square minus h square u square plus c square d phi square h square du equals to h square du square, or u square c square into u square c square minus h square d phi square equals to h square du square, or d phi square equals to h square du square upon u square into u square c square minus h square. This is equation 6. Or d phi equals to plus minus h upon h into du upon square root of u square c square into u square c square minus h square. This is equation 7. This gives the first integral of the differential equation geodesics on the right helicoid. Case 1. If u square c square minus h square not equals to 0, the integrating 7 we get the equation of the geodesics as phi equals to g plus minus h equal integral du square root of u square c square into u square c square minus h square, where g and h are the arbitrary constants. Case second, if u square c square minus h square equals to 0, for 6 we have h square du square equals to 0, or h du equals to 0, or du equals to 0, or u equals to constant a say, or f equals to 0. Hence the curve u equals to a geodesics if and only if g is a function of u only, that is if g1 is 0, g equals to u square c square, or g1 equals to 2u, therefore the curve u equals to a is a geodesics if and only if 2u equals to 0, that is if and only if 2a equals to 0, because u equals to a, that is if only if a equals to 0. Hence the parametric curve u equals to 0 is also a geodesics on the right helicoid.